Hey guys, welcome back. So this lesson is the first part of our 7.5 lesson, which is solving, we're going to be solving exponential equations in this one. And then our follow-up lesson is solving logarithmic equations. So we have a couple of different methods for solving exponential equations. And the first method that I'm showing you is basically equating the bases, but we call this the baby base method. Unfortunately, the baby base method, while it is very amazing, is not always something that you can actually do. So they have to have a common base. And if you remember last semester, and I'll post it again, but we had a chart of perfect squares and cubes and fourths and fifths. And that chart would help you immensely if you're trying to find if there's a common base. So what you would do on that chart is you would look for a row that has both a 6 and a 216 in it. And it turns out there is a row where both 6 and 216 show up, and it's in the row that's called the 6. So what we're going to do is we're going to rewrite each base, which the bases are the 6 and the 216, so that they are the same number. So we're going to keep the 6 as a 6, but we're going to rewrite the 216 as what it is as a base 6, which is 6 to the third power. So 6 to the third power equivalent to 216. Why would I want to do that? Well, think about this from a math logic standpoint. 6 to some power equals 6 to some power. The only way for that to be true is if your exponents equal each other. So once you can maintain the same base, that means the exponents have to equal each other. So now we're going to set up 2x minus 7 has to equal a 3, and then we just solve the simple equation. So I'm going to start by adding 7 to both sides. We get 2x equals 10, and then of course we're going to divide by 2 on both sides, and we end up with x equals 5. Okay, so if we kind of go through those steps one more time, we rewrite with common base or with baby base. And then we equate, so that's the fancy word for set equal to, equate the exponents. And then, of course, we solved. With an exclamation point, you know? All right, so same idea here. Now, this one always trips up kids because they're like 4 and 8, and they think they know what the common base is. Everyone assumes it's a 4. So I would challenge you, 4 to what power is an 8? And you might be thinking about that for a minute. If you look on your chart, there's no row. Well, I shouldn't say that. There is a row that has a 4 and an 8, but it's not the row of 4. Look up higher in the chart, and you'll see it's in the row of 2. So what we're going to do is we're going to change our bases, which are 4 and 8, and we're going to change them to 2's. So 4 is really a 2 squared, but it already had an exponent of 3x, so we got to leave that there. And then 8 is 2 to the third power. But that number already had an exponent of x plus 1. All right, so this problem has another layer of fun to it. It had existing exponents, which means before I equate the exponents, I need to simplify the exponents. So right here and here, I need to simplify the exponents. So think about your exponent rules. If you have a power raised to another power like that, we multiply them together. So this side becomes 2 to the 2 times 3x would be 6x. And then this side over here would be 2 to the, now careful on this one, it's 3 times the entire exponent of x plus 1. So we'd have to distribute that 3. So that would be 3x plus 3. Okay, now that we have the same base with exponents, we can set our exponents equal to each other. We can equate the exponents. All right, here goes. So we end up with an equation, 6x equals 3x plus 3. And then we simply solve it. So I'm going to subtract 3x from both sides. Oops. We get a 3x equals 3. And then, of course, divide both sides by 3, producing an x equals 1. Not too bad, right? I know there's a little bit of exponent work at the beginning. These, again, I know I've been saying this a lot, but these questions show up on the No Calculator SAT quite a bit. They really want you to understand the properties of different functions that we run into and how you can reword them or rewrite them in a way to work for you. And of course, it all has to be done without a calculator. because that's life, right? All right, so now what if there is no common base? What if I look on my chart and I don't see a common, it's not in the 2 row, the 3 row, the 4 row, it's not anywhere on my chart. Well, this is a method that actually would work for any problem, even the common base questions. You can always apply a logarithm to each side of the equation. So when I say logarithm, I want to use a logarithm that's easy for me to access. So I'm thinking, okay, calculator, right? I've got the common logarithm and I've got the natural logarithm. Remember on your calculator, the log, that's the common logarithm, and then the ln, that's the natural logarithm. Because I don't want to be messing with other bases and worrying about that, I'm just always going to use the common log or natural log. We'll discuss this more in the meets, but I literally only use natural log with like one exception. And the reason is because natural log has 2 letters and it's less than 3, so it's less writing, and that's why I use natural log like all the time. I know that's not a good reason, and we'll share a story with you in the meets about my children's name and how this all relates to this lesson. I don't want to put that out on the internet. My kids get so embarrassed by the story, so I'll tell you in the meets, okay? All right, so big note, it does say here you must isolate the base before you do any work with logarithms, so keep that in mind. All right, good news. The base, which is 2, 2 to the x power, like that term is isolated, so we're ready to apply a logarithm. So again, you can choose. You can apply a natural log or a common log, and if we were in class, we kind of take a vote. Do you want to apply a natural log or a common log? And since it's just me here doing the lesson, I'm going to go with natural log. Okay. So the natural logarithm is, remember, ln, and in math, if you apply something to the left side of the equation, you have to apply it to the right side as well. Why would I want to do that? So this comes back to the last lesson, the properties of exponents. When you apply a logarithm to something with an exponent, that allows you to take your exponent and write it down in front. It brings the exponent down, which is exactly what I needed to have happen, because now what I have is the natural log of 2, which is just some icky number on my calculator, and then it equals the natural log of 7, which again is some icky number on my calculator. So if my goal is to solve for x, I am one step away from that. All I have to do is take this icky number, natural log of 2, and divide it over to the other side. So I don't want to type yet, because I definitely don't want to round off any icky numbers. So I'm just going to use the natural log in my work until I'm ready to type. All right, these are canceling each other out. Y'all, I am ready to type. I'm going to type this on my calculator. Doesn't that look like the change of base formula? Sure does. All right, I'm going to show you something in a minute. But first, let me start typing. So it is the natural log of 7, close the parentheses to stop the logarithm function, divided by the natural log of 2. Make sure you use the same logarithm. And we get 2.807, blah, blah, blah. Icky. Now, remember earlier I said it didn't matter if you used common log or natural log. So if you went rogue and you used common log in your math, and you ended up with common log of 7 divided by common log of 2, well, looky there, you get the same answer. So when I say it doesn't matter which logarithm you use, which button, it really doesn't matter. The only thing that matters is that you use the same one in your ratio. Now, if you can connect to the last lesson, man, it looks a lot like the change of base formula. It is exactly the change of base formula. And in a meets, we'll prove how the change of base formula works, but it has to do with this. So I remember when we were, I forgot the answer, 2.81, I'll say. I don't know if it said to round elsewhere, but that's my answer. Earlier when we were learning the properties of logs, that exponent property one felt really useless. We're like, why are we doing this? Like, what a weird property. It's actually the basis of our work with logarithms. Like, why would I even want a logarithm function? To undo an exponential function. So that's the whole point of a logarithm. It's actually the most important property. The other ones are just kind of amazing because they work out with exponent rules. All right, remember that big note at the top of the notes? It said, you must isolate the base before you do any logarithm work. This is a good example of that. So we need to isolate the base, which is the 10 to the 2x power. 10 is the base. But the isolation step would be right here. We're going to subtract 4 from both sides. So we have 10 to the 2x power, and then it equals 16. Now, I said there was only one case where I would use a common logarithm, and this is it. So the reason I would use a common logarithm is because one of my bases is a 10. And remember what happens with common logs and 10s? They quickly cancel each other out. So I'm going to say, so first here I'm going to write a note that we isolated. And now I'm going to apply, I'm going to use the common log even though it hurts me to do it. I'm going to use the common log, apply it to both sides. All right, so common log here and common log here. Now, if you went ahead and typed the common log of 10 in your calculator, it would produce a 1, and that's why we say it cancels. So if you want to think of it that way, that's great. So right here, this cancels out to a 1. The 2x would come down, right? That's the whole point of the logarithm, the 2x would come down. And then it ends up being log 16. Now, guys, that is not anything pretty. Common log of 16 is yucky. But if I think about my math, my next step here would be to solve, right? Divide by 2. All right, back out of here. Go back to my calculator. It was the common log of 16. And then it wasn't divided by the common log of 2. It was literally divided by 2. And you get that answer. Now, earlier in the work, remember how I said it was common log of 10? If you were to type the common log of 10, see how it's a 1? So that's the canceling right there. I'm not saying they're all going to cancel, but when you notice something canceling, like, ooh, that's awesome. I forgot the answer. Okay, try again. Where are we at? 0.6. Did it say word around? Of course not. All right, let's go 100th place at least then. 0.60. All right, good work. So we ask ourselves, okay, who's the base? It's the number e over there. Is it isolated? And the answer is no, it's not isolated. So we're going to start by taking the 5 out of the left side by dividing by 5. So I'll write myself a note that we isolate. So now I end up with e to the x plus 3. And then equals a 9. Now, if we're in class, Mrs. Meyer would tell you that her favorite logarithm is the common logarithm. I don't know why, it's clearly worse. But even she would use a natural logarithm on this question. And you might want to say, why would she use a natural logarithm even though she doesn't like it? And look at that base. Who's the base of a natural logarithm? The e, the number e. So we're going to apply a natural log to both sides. So natural log, natural log. The reason we went with natural log is because right here, the natural log and the e will cancel. Again, they're not always going to cancel, but in this case they did. So the x plus 3, the exponent, is going to come down no matter what. I'm not going to bother saying times a 1 because natural log of e is 1, but that's silly. I'm just going to leave it alone. And then the natural log of 9 is some number on my calculator. So if you wanted to, you could type this on your calculator right now. If you love writing decimals, you go right ahead. You're going to have to type at some point. I forgot what I'm typing. Natural log of 9. All right, natural log 9. I'm going to go 197. I know that's silly, but that's what I'm doing. And then last step here, we're going to subtract 3. Now all of this arithmetic, if you want to call it that, ends up on my calculator anyway, so it's not like I'm doing mental math here. And please, for goodness sakes, guys, do not start subtracting decimals in your head. It does not end well. Negative 0.80 is where I'll round. Again, they didn't tell me where to round, I don't think, anywhere, so we have to at least agree on the hundredths place. The more decimal points you give me, the more place values, the more accurate your answer. So, of course, if you gave me more, that's even better. Okay, good deal. Oh, was that it? Well, okay, never mind. I guess I'm done, guys. All right, so just to recap, we had the baby base method. It's great, and it works sometimes. So when you practice this on a worksheet for us, we'll indicate, like, hey, here's a bunch of problems that you could use the baby base for. But some people say, do I have to use the baby base? Because I really love this logarithm method. You can use the logarithm method on every single question. I will warn you, though, that sometimes, depending on how exciting your exponent is, your math gets a little difficult. So if you see the baby base as an option, I encourage you to use that method. When it comes to applying a logarithm, Couple of rules to remember. You must isolate the exponential piece first, the base with the exponent. Once it's isolated, you can decide to use a common log or a natural log because of the buttons we have on our calculator. Technically doesn't matter which one, but if you're wise and you choose the right one on certain problems, you'll see some cancellation happen. If you are a stubborn mule like Mrs. Abruzzo and you only want to use natural logarithms, so be it. Everyone knows natural log is better. Okay, I'm just going to say bye.